In this video, I'd like to look at Mathematica and do some, I'll call them simulations, develop some intuition around z-scores and how they scale with the number of samples and confidence intervals and so on. Okay, so first I'm going to just start off with a property of normal distributions if you sort of add two normal distributions. So if I take uh, if I take a number from a normal distribution and another number from another normal distribution and add them, then that result can be thought of as coming from a third new normal distribution where the mean is the sum of the means, and the variance will be the sum of the variances, but I'm going to work with the standard deviation, so that will be the square root of that. So here's just this result in Wikipedia, so you don't have to look very hard for it. So they're working here with the normal distribution of the mean and the variance, and they have one x and one y, and then they're adding the two quantities, one that came from the x normal distribution, the other one that came from the y normal distribution, and that quantity can be thought of as coming where the mean is the sum of the means and the variance is the sum of the variance. I'm going to work with square roots, so I'm going to have a square root around that. Okay, so so I'm just going to I don't want to think I have any sort of special numbers up my sleeve. So I'm just going to get some random numbers for the first mean and the first. So I'm just using random real number between 0 and 10. That'll be my random mu. That came up to be 9. How did I change that? How did I end up with that? Okay, so that was, I got a random mu for a random average. And then let me get sigma. And then let me get another mean and another standard deviation. So I just pull them at random. And now I'm using 4. I'm going to do 500 samples. I'm going to get, I'm calling this combo. I'm getting a random, a single sample from the first distribution and the second distribution. And I am adding them. So here's random variate and then plus the second random variate. And I am adding that combo to a list. So I'm just getting 500 samples of this sum of samples from the random normal distribution 1 and normal distribution 2. And let's make a histogram of that, and I'm naming it H1. So there it is. And my numbers ended up to be large, so it's centered up here. So maybe I should have gone farther than 25, but I'll just leave it. It's the mean for this was 18. If I add the two mu's, it's 18. There's some, it's random, so they're not exactly right, but they're in the same ballpark. The standard deviation of my list is 4.94. If I do this square root of the two standard deviation squared, so get the sum of the variances and then take the square root to get the standard deviation. And so we see a fair amount of consistency there. And then I'm going to plot the normal distribution, the theoretical average and the theoretical standard deviation over the same range, 0 to 25. And then plot them together. So So there it is. So there is this idea of summing uh, two normal distributions and getting a new normal distribution with the sum. The mean is the sum of the means, and the variance is the sum of the variances. Okay. So far, so good. Okay. Now, adding, instead of having two different uh, normal distributions, I'm going to take, say, from multiple samples from a given distribution. And then instead of just summing them, I'm going to take their average. I'm going to take their mean. So uh, I'm going to vary this quantity j, but the number of samples I'm going to take is j. I want to see how this depends on j. So first I'll just take one sample, then I'll take two samples, then I'll take three samples, and I'm appending them to my list. So I'm going to get 5,000 samples of when j was 1, just one random variable. When j is 2, two random variables. When j is 3, three random samples from the same distribution. And I am getting the uh, standard deviation. So I'm figuring out I'm adding the number of samples, j, and the standard deviation. So I want to see how my standard deviation of this mean varies with the number of samples I take. Okay, and that's supposed to be 1 on the square root of n. And I just want to sort of show that. And you can sort of see that in the previous example where I just had where we added two normal distributions, got another normal distribution, that was adding them. Now I'm taking the mean, so I'm dividing by n, and then it's the standard deviation. So that ends up sort of, that's where this, so the mean is it's not, I'm adding, but then I'm also dividing by n, and the same thing with the sort of the sigmas are going up by sort of a square root of n. It's the variances that add, and these are all the same variances. So the variance would go as n if I were just purely adding them. So the standard deviations go like the square root of n. But when I take the mean, then I've got an n in the denominator. So it's going to end up to be sort of 1 on n to the, 1 over n to the 1/2, n to the minus 1/2. Okay. So run that, and I am getting, and I just still have my random mu and my random sigma. So I don't want this to depend on anything in particular. And then, but I ran through that, and this was one sample. What was the standard deviation? What was the sort of average standard deviation? What if there were two samples? What was my average? So I want to see how the standard deviation is scaling with this number of samples. And here I get, so it is dependent on the standard deviation of the original sample, and then it comes down, and that is an n to the 1/2. I have here, I call that data my SD. So I made a list, and then as I simulated over, and this was going over 20 different sample sizes, and then for each sample, I got 5,000 samples, and figured out did that average over the J samples, and did that 5,000 times and got their average and added it. Okay. So you get the idea. So now I'm fitting that data to a power law here. So I'm doing a find fit. I have my data and I'm comparing it to a power law form, and I'm going to find a and n as parameters. The variable is x. And there we see this first number depends on my original normal distribution and its standard deviation. So it's about the same. So up here in out 3, that was my original sigma 1, that was 3.6. And so I'm getting that sort of back again. And then this power is the minus 1/2. And that's what I wanted to show. That's what I was interested in, that 1/2. I want to get these individual numbers out of my find fit result up here. And I'm using this slash dot here so I can get out of my fit the coefficient and the fit. And this varies depending on the random numbers that were selected, but this always ends up to be somewhere in the vicinity of minus 1/2. And then I'm plotting that mathematical fit and then putting them together. So we see, and that is like an excellent fit. So this is how the standard deviation is depending on the number of samples. So as we increase the number of samples, we are bringing down the sort of spread, but it comes down fast in the beginning with the number of samples, and then it kind of slows down, but it's always, more is better. So it gets the standard deviation of the sample is, squeezing down from the original standard deviation to as the square root of n. Okay, so now I want to sort of start talking about confidence intervals. So there's a concept in statistics of confidence intervals. And so you have, in this case, in sort of what is known as a z-score, you have some distribution. And the idea here of the normal z-score idea is that you have a sample that you are, a distribution that you are drawing from, and its standard deviation. So sigma comes from the overall sample that you are pulling from. And then you pull some number of samples from this distribution, and you want to know, do you have confidence that the average, you want to have confidence that you don't know the game is I know the standard deviation of the sample, but I don't know the mean. How this occurred, I have no idea. But that is the idea behind this. And then you do better with, instead of you move from z-scores into a t distribution another time. But here you assume that you don't know the mean of the distribution, but you do know its standard deviation. And then you are building this confidence interval. So you take a number of samples from the overall distribution, and then you calculate the average of those samples, and then you do sort of a plus minus. That mean of those samples should be close to the overall mean. And I want to sort of say I want that with a confidence. I want to be right 95% of the time. So we saw that n is the number of samples. So we saw how when we increased n, that the spread, the standard deviation of that mean goes down as the square root of n. So there's our sigma, there's our square root of n that we understand. This is the mean over the samples. And then we have this concept of the z, sort of how far away from the mean in the sort of original normal distribution do you have to go to come up with the 95%. So And then people talk about one tail or two tails. Um, and so we're going to do the sort of two-tail approach. And so there's a standard number for 95% confidence here of 1.96. So if that Z that we saw above, so the sigma was whatever it was for the distribution, the square root of n, we tested that behavior and we sort of have some confidence in it that at least we've simulated it and saw it in action. Then the Z comes from just integrating a normal distribution and a bell curve, and we see that 1.96 they say is for 95% confidence. And so you take your samples, you take the average of your samples, and then you think that you say that the actual mean of the distribution lies somewhere between that range of plus z sigma divided by the square root of n and minus z sigma squared of n from the sample average. Okay, so back over to Mathematica, and this is what we want to test here. So I'm going to change the number of samples at different times. So here I have it as 3. This is a variable I'm calling am in. I am in the, and it's just going to sum. So I'm going to sum up the number of times that I am in, that my actual mean is in within the plus and the minus of the sample mean. Okay. So that is set to 0, so I can sum over it, and I want that to come out to be sort of 95% of the time. I'm taking, in this case, I set it up that I want sample number. I can then vary that. Here's this confidence. I'm looking for 95% confidence, so that was the 1.96. And then I have a bunch of results. And in the end, I'm just going to print out this am but I could print out this result out. So there's a lot more information in result if we want to look at that. I'm looping, I'm going to go over 1,000 samples. So if it's 95%, I expect sort of 950 of them to be right, to be in this range. Okay, so this is just a centered for loop. Start I at 1, go up to stay in the loop while it's less than or equal to 1,000, increment by ones. Okay, I am changing mu. So I'm not doing this for a fixed mu. I'm going to keep changing mu. I'm going to keep changing sigma. Could fix them, but I just decided to go all over the place. I am taking random variate normal distribution sample number. So that's getting me, in this case, 3 values from this normal distribution, and I'm averaging. And then I'm creating a sort of a list of lists. And I start off with this data point, which is just a blank list. I add to it the mu, the average for that normal distribution. I add it the sigma, so the first point, the first value of this is the distribution's mu. Then the second one is the distribution sigma. And then the third one is the average, and that is over the 3 samples. Okay, and then the question is, are we or are we not? How does average compare to the average of the 3 samples compared to the average that we know going in from the distribution? And so I say here, I'm using in Mathematica's if. So here is if the sample average is greater than my average over my, in this case, 3 samples, plus the standard deviation times my 1.96 divided by the square root of the number of samples. I'm going to say 0. So if it's above the average plus, so, then I'm going to say 0. I'm not going to count it. It's not, it's outside of my range. Otherwise, so it's always if some question, what you do if it's true, what you do if it's false. If it's false, I'm going to ask another question. I'm going to say if I'm less than the average minus the sigma, the 1.96 divided by the square root of n, also a 0. And then the final otherwise is a 1. These are going to be mostly ones. 95% of the time I'm expecting ones. And then I am incrementing my m in sum with this within. So the within is a 0 or a 1. And then I'm adding to this data point the within, and then appending all of my data, which was the mu and the sigma and the average, and whether or not it was in the confidence interval. I'm adding them all up into result. And I don't print out result, so you won't see it, but I could. But what I am printing out in the end is this m in. And again, I had 1,000. There it is. I had 1,000, and I'm looking for 196. That's supposed to be 95% confidence. So I'm looking for this to be in the ballpark of a 950. So 957. Let's do it again. Okay. If I want to show you all those things I'm collecting, I can do the print of a result. Another semicolon in there. And then this is going to give me the 1,000 of the list of lists and all the individual. And so the main thing that takes longer is the sort of the printing more. So I was calculating all these things before, but I wasn't showing them. So it's really the showing them that takes so long. But so this was each one of these. This is the average. This is the standard deviation. This was the average and from the 3 samples, and then this was whether or not we were in. So we're expecting mostly ones. And then let's take that out, and let's just change the number of samples to, say, 5. And remember that here's where that number of samples, the number of samples appears here, and that the number of samples I'm taking, but also here in how we scale the sigma. And so if we are scaling it in the right way this shouldn't have an effect if we're scaling it the right way. So it should still be in the ballpark of the 95%. So 950. And there it is. In that case, right on the nose. So that's what I wanted to show, to play with this idea of the z-score and the confidence interval. And my main interest, if I'm being honest, is to sort of convince myself of how this scaling with the number of samples that went down. So if I took n samples, then the standard deviation of that average over those n samples, its standard deviation was going down as 1 on the square root of n. All right, that's what I wanted to show with this one. Thanks for your attention.